Hi everyone, welcome to this video on lesson 16 of the atomic structure and periodic table scheme of work. This lesson is about transition metals and it's building on some ideas that we have kept coming back to throughout this curriculum. So we actually introduced the structure of metals in very rudimentary terms all the way back in year 7 in the particles and energy scheme when we were looking at thermal conductivity, thermal conduction, and this idea that metals have these extra particles which allow thermal energy to be transferred more quickly. We came back to it in year 8 when we looked at electricity and why it is that a potential difference drives a current. So that's looking really at electrical conductivity. We're looking at it today and trying to explain the structure of metals in terms of what students have learned about both atomic structure and the periodic table. And we will come back to it next year, and if you've taught chemistry before, you'll know students have to answer lots of questions about metals and structure of metals and how that relates to their properties. So we're kind of touching, this is a soft introduction to that what we do in the structure and properties unit, this lesson today. But what I want to emphasize in this lesson when I'm teaching it to students is kind of why we get this delocalized electron structure within a metal. So I'm just going to start with a relatively simple everyday example. I might start by just asking students what they know about metals. Can you name any metals? What might metals be used for, and so on. One really obvious use, once you've spoken to them a bit about that, one really obvious use that we can refer to, and it's going to be really helpful for the kind of properties that we're looking at in particular in this lesson, is a copper wire. So here's my copper wire, and what I want to do is zoom in on this. As always, I'm going to zoom in, and I'm going to build up the picture, because they've kind of seen this picture before. What I want to do in this lesson is give them a sense of why we have this picture of metals based on what they now know, having studied this scheme of work. So if we look at the wire here, let's just do some particles inside here. Let's start, and we always start with their kind of prior knowledge. You might want to ask them to sketch this on whiteboards first, but what you would hope is all of them will have this very kind of year 7 picture of, well, I know a copper wire is a solid, therefore you're going to have these this fixed lattice of particles, neatly arranged, not moving, only vibrating, so on and so forth, all of that stuff. And what we want to do though is say, well, okay, if these are all copper atoms, if this is a piece of copper wire, and maybe it's worth me emphasizing this, so let's write copper wire here. This is a piece of copper wire. That means these are all copper atoms. But let's zoom in on one of these copper atoms and look at what's going on here. So I'm going to zoom in, in fact I'm going to zoom in on one down here, just to make it easier for myself later on. So I'm going to zoom in down here and look at what's going on with one of these copper atoms. And again, as we've seen in the previous, in a couple of the previous lessons, we're going from concrete to abstract. So we're starting with the copper wire, something they should all be relatively familiar with. We're moving to a kind of simple picture in terms of almost like Dalton atoms or particles. I'm just going to get rid of this because that's not very neat. And then we're going to an increasing level of abstraction. We're talking about what we've learned about in this unit, which is electron configuration and so on. Now, copper is a tricky one, and all the transition metals are tricky because they don't really follow the 288 rule. Again, when they get to A-level chemistry and university chemistry, they start looking at all those SPD shells, all of that stuff, so it gets a little bit more complicated. But we can gloss it a bit, and because essentially we just want to give them a sense of why it is that they have this structure that we've seen already. So I'm just going to say, well, look, copper atoms look something like this. If we zoom in, they've got a certain number of shells here, and I'm just going to do a kind of dashed line like this. So they've got a certain number of shells like that, and you know there might be quite a few shells here, but we're not too interested. But then on their outer shell, and again I'm keeping this really simple, the purists may not be happy with this, but I just want to give students some sort of mental model about why we have this picture. essentially we've got various shells in here. Maybe rather than the dashed lines, it's easier if I just draw a few shells like that. That's not really important what's going on here. What's important, as we keep coming back to in this unit, I suppose it's the big idea that links a lot of these lessons together, is that what matters in terms of chemistry is what's going on in the outer shell. And what I'm going to say is, again, very simple terms, we can think of, in simple terms, copper having 2 electrons in its outer shell. Now, because you've got all of these copper atoms together, what copper likes to do when it's in its kind of pure form is, what happens is, these 2 electrons are discarded. So we've got 2 in the outer shell. We've been telling students that atoms like to have a full outer shell. So how do they get a full outer shell? Well, they get rid of these 2 outer electrons. And what that does, we can tell students, is these electrons become what we call delocalized. So I'm going to label this here and say these electrons become delocalized. And that's a really important word. And again, you can kind of look at what that word means, and they were in their local area, they're now not in their local area. And again, you may just wish to tell them, or you may wish to write this down. What delocalized means is, if these electrons have become delocalized, is that they're shared between all of the atoms in the lattice. So I'm just going to add a note here to say shared between all atoms in lattice. So depending on who's taught them in year 7 and 8, they may have come across this word delocalized before. I often refer to them as free electrons, but now we're using even more sophisticated language because we can explain why this happens in terms of atomic structure. So these electrons become delocalized. That means they're shared between all of them. And what I might do there is then sketch this on here. I might even do this in a different color. Well, yeah, let's just do it in this color. Again, you can decide what you want to do, but I'm going to show this again, draw students' attention to the fact that this representation I've done here is kind of 2D, so it's not the best, because actually what we've got is a 3D lattice and these electrons are going to be all over the place. But I don't want to kind of confuse things by drawing electrons inside other atoms. I think that might complicate things more than we need to. But then we can emphasize to students that these electrons here, these are delocalized. So again, I might just put something here like delocalized electrons, just to really stress that's what we're talking about, that these electrons have been donated by atoms and they are now shared between all the others in the lattice. But of course the story doesn't end there, because what we can't do is just have random electrons and not tell them about the other side of this, which is that, well, okay, look, if this copper atom has got rid of its outer 2 electrons, then it's going to become an ion. We know that. We've seen that on multiple occasions now. I'm going to draw these multiple shells here, like this. I'm going to say the outer shell has been lost. Again, I'm not worrying too much about the number of shells. You can just say, look, there's a lot of electrons in between. Don't worry too much about those. What mattered was that it lost its outer 2. But what I want to say here is, and again, this is a really good opportunity to revisit prior knowledge and check students get this idea of ion formation. What's the charge? Is it positive or negative? Well, it's positive because they've lost 2 electrons, and it's plus 2 because they've lost 2 electrons. So I'm going to put 2 plus here, like this. And then the point we want to emphasize is, well, okay, if you got rid of your electrons, we've seen how they're now scattered around the lattice and being shared between all of these particles. And the particles themselves are not atoms anymore, they are positive ions. Now, it doesn't really matter how you do this. I'm going to do it like this. I'm going to say all of these in copper are Cu2 plus, and this is how we write it, Cu2 plus. Now you might not want to label all of these because that would take you forever. But what you want to do is map students' understanding of what's going on onto the diagrams they're probably familiar with from years 7 and 8. And again, you'll see in the slides, you tend to get diagrams like this. I can just sketch it over here. Something like this, where you've got, you just have these big positive ions and the delocalized electrons kind of scattered around like that. And what you want to do is show students how what we're talking about here is exactly the same as that. We've just explained why we have those positive ions. Why these are positive and not neutral? Well, it's because they started out as atoms, but they donated their outer 2 electrons to be shared among all the other atoms, which we call delocalized, and therefore that's why you have these positive ions. I might add positive ions here, like this. So again, we're really just giving students a picture of why that is the case. So that's the structure. The final thing to do is just talk about the properties. So again, you can say, well, look, because we've got these delocalized electrons, these are free to move, and they can move all over the place as follows. And that is what allows them to be really good conductors of electricity and conductors of thermal energy. And again, if you want to revisit some of that stuff that you did in year 7 with conduction, and year 8 to do with conducting electricity, that's fine. I'm just going to leave it there. The other thing you can say is, and again, this is something that's going to be covered in more depth in the second unit of chemistry of the GCSE, but you can kind of touch upon it now, is what you can say is that because you've got these layers, and they're not bonded together by really strong bonds, you've got these delocalized electrons that are kind of shared between, you can essentially say they act like a kind of oil which allows the layers to slide over one another. And you can label that and say, because those layers can slide, and I've shown this and I've talked about it, then the word that they need to use is ductile, and that's what allows copper and other materials, a lot of the other transition metals, to be drawn into wires. Now the extension here is about alloys. That's what we're going to come on to in the next lesson. So you might want to say, sometimes actually for some things we don't really want our metals to be kind of bendy or ductile, malleable, whatever we want to talk about. So let's say, I don't know, an aeroplane chassis, or a bicycle frame, or whatever. And you can just bring in the idea of alloys and say that actually these are really useful in some ways, but there are some uses where actually these properties aren't that helpful, and that's why we mix them with other metals. So that's an extension in this one that you might want to mention as an aside if you've got a group that really asks lots of questions. Otherwise, that's what will be covered in the next lesson and the next video, which is the final one of this scheme of work.